So again, if you want to do your notes in OneNote, that's perfectly fine. If you want to do them by hand, that's perfectly fine. If you just kind of want to sit and listen, again, that's perfectly fine. You kind of do whatever works for you. And if you want to experiment a little bit about like what works best for me, you're perfectly entitled to kind of change whatever you're doing. I think that's all important for you to figure out, especially, some of us are, we have juniors and sophomores in here. Those of you that are juniors, it's not going to be too long before you're on your own off at college. So it's nice to have kind of figured out, like what works for me in terms of being in a classroom, because no one's going to tell you how to do something, like take notes or study or whatever once you get off to college. They're going to be kind of expected that you have most of those soft skills kind of figured out. So now is a nice time to do that, particularly in this class where you still have all my notes, you still have recordings of all the lectures. So if you're going to try to see if maybe if I just sit and listen and I use this other person's notes, maybe that works better for me, now would be a good time to kind of figure that out. Or if you're like, I know I can't pay attention if I'm not kind of writing stuff down, and also then now is a good time to figure that out if you don't know that already. And certainly I'm that kind of a person. It's pretty rare that I can just sit and pay attention unless things are moving so fast that I can't pay attention and write things down at the same time, in which case I'll skip the writing things down. It's more important to pay attention so I can understand what's going on. I've had 1 or 2 college classes where it's just I've given up on taking notes because everything is moving too fast and I can either write things down that maybe I can understand later, or I can sit and just try to pay attention and understand now, and we'll worry about the notes later. And that was the much better option for me in those couple of times. But normally I am, things are moving at a speed in which I can do both. But if it gets to a point where it's either I can write it down or I can pay attention, I usually opt for paying attention. With the hope that I can, if I need to find somebody that's written it down later, I can find somebody else that's written it down later. And in this class, that's no worry because you have, exactly what I've written down, But just an aside, a little story about me. So today, we had been talking about sets last time, right? Today we're going to talk about a special kind of set called a relation. So a relation is a set of ordered pairs. Again, when we say ordered pairs, we really mean an XY, right? Okay. For this relation, the X values are coming from some set D, and the Y values are coming from some set R. And we call this set D the domain. And the set R we call the range. So just as a little example, so a relation is just a kind of a set, so we'll name it with a capital letter. And then we could use the squiggly brackets there. And then maybe we say that my relation just contains these 4 ordered pairs, 1, 2, 2, 3, 3, 4, and 4, 5. Is everybody okay there? So in this case, the domain, or the set D, it's just going to be the x-coordinates from my relation. And that means my range, or my set R, is going to be the y-coordinates from those ordered pairs. And since this relation is a finite set, the domain and range are just going to be finite sets, so I can just list the elements individually. Is everybody okay with that idea? Where could I get into a little bit of trouble here? Let's look at a different example here. Did you get it?
Kind of.
Kind of. Are you back? Do you have?
Just kept blocking me from everything. And then she's putting on the guest Wi-Fi.
Oh, okay. So we've just started notes. If you have to finish up the homework quiz stuff, I don't know. Were you?
No, I was trying to pin it in the time.
Okay, so just go ahead and finish handing that in here real quick, and then you can jump in.
Okay.
Okay. So again, everything that I do in class we record, and I post the notes are all in the content library, so you can view those later also. So if you've missed here 10 minutes or whatever, you can go back and check that out. Okay? Yeah, no problem. Okay. So let's look at this relation B. Still a relation. It's just a set of ordered pairs. What do I have to be careful about, though, when I write the domain? Remember, the one restriction for a set is that we can't have any repeated things in our set, right? If I look at the domain for B, I have some repeating going on. Now that's fine for the relation, but when I write my domain, how many times should I write down the number 1? Just once. So even though that 1 happens 4 times in the relation, when I write the domain, just 1 time do I write it down. So it's easy to kind of forget to do that, which is why we did this example, to kind of remind us that when we write down a set, there is no repeated items in our set. So even though 1 happens a bunch of times in the relation, it's okay because each ordered pair in the relation is different, right? So we didn't violate any rules when we wrote down the relation because all the ordered pairs are different. What we have to be careful about is when we write down the domains and ranges, that you could have parts that are repeated there that you need to make sure you don't write down the repeated pieces. Everybody feel okay about the domain and the range and the relation? Okay. And for the start here, we're just going to talk about these finite, or the relation as a finite set. We'll talk about the relation as an infinite set the second half of today or maybe next time. But we're going to start with just the finite situation because it's a little bit easier to deal with. Everybody's okay with that plan? Okay. There are 4 ways to represent a relation. So the first way is what we've seen in that previous example where we just use a set of ordered pairs. And we can, especially if it's a finite situation, it's very easy to do that. We can just literally list the ordered pairs that are involved. The second way is with something called a mapping diagram. And for a mapping diagram, what we do is it's kind of a visual representation of that relation. So we draw like an oval for the domain, and we'll draw another oval for the range. And then inside the domain, we'll put the numbers that are in the domain. And inside the range, we'll put the numbers that are in the range. And then we'll use an arrow to show how those numbers are paired together. So if I wanted to translate this mapping diagram to a set of ordered pairs, I'm just going to look at the arrows. Each arrow is going to represent an ordered pair. So this first arrow that I've highlighted in yellow represents the ordered pair. Do like an arrow there. 1, 1. Right? The arrow that I've highlighted in blue represents the ordered pair 2, -3. And the arrow that I've highlighted in green represents the ordered pair 3, 1. Everybody okay and can see that this mapping diagram is really describing the same information that we had with the set of ordered pairs. It's just kind of a visual representation rather than a symbolic representation. You okay there? Okay. Our third example is with a graph. So if we're dealing with a finite relation, our graph is just going to look like points, just points plotted, right? So in this case, our relation has 5 ordered pairs in it. We have 5 points. But you know that graphs don't have to just look like points. You could have some connected line going on through here. And hopefully you remember from your geometry class that on any line or even any line segment, there's infinitely many points on that, right? So if we have any kind of line segment, we have an infinite number of points on it. That means that our relation has an infinite number of ordered pairs, which makes that relation an infinite set, right? So we have to be a little bit careful there because the way we describe a finite set and an infinite set would be different. So we have to be a little bit cautious about that kind of thing. But we'll do a bunch of examples here in a few minutes to kind of help get us comfortable with that. And the last way is with an equation. Now, if I have a finite relation, it doesn't really make sense to describe it as an equation because typically equations you can like plug in any value for x to find a value for y sort of thing. So if we have something like this, which you probably recognize as the equation for a line, we know a line has infinitely many points, so this certainly makes that relation infinite. And really, for equations, we wouldn't bother to use an equation to describe a relation unless it is infinite. Okay there? All right. Now what I'm going to do is I'm going to introduce a special kind of relation called a function. So because a function is a relation, we know a function is also a set of ordered pairs, right? Where the x's come from a set D and the y's come from a set R. So we say a function is a relation where every member of the domain is paired with exactly one member of the range. So what we're going to do here now is we're going to do a bunch of examples where I'm going to come up with a relation in some of these different forms, whether it's an equation or a graph or a set of ordered pairs or a mapping diagram or whatever, and we're going to decide whether it's a function or not, right? Because some relations are functions, but some are not. Everybody's okay with that plan? Just to kind of get us comfortable with these different representations and deciding whether something is a function or not. And we might come back and take these afterwards, depending on how much time is left. Come back with these examples and then pick out the domains and ranges after, depending on how much time. So if you're leaving space for the examples, we might come back and reference these examples again with the domain and range today. So I don't know, just as you're writing your notes, keep that in mind that we might come back to these, so leave a little bit of space to write some other note next to them. Okay with that idea? Just to give you a heads up, some people are very picky about how neat their notes are, and I don't want to give somebody a stroke trying to erase a whole page of notes here because they didn't leave enough space to fit something in or whatever. Okay, so let's look at this set of ordered pairs that we looked at just a moment ago, right? We already talked about, or we already saw this set of ordered pairs when we were talking about a relation, as I used it as like a nice little example of describing where the ordered pair, what do I mean by ordered pair, set of ordered pairs, and where the domains are and the ranges and all that. But right now, we're trying to determine whether this is a function or not. Right? So I am mostly concerned in a situation like this that each x is paired with exactly one y. So basically what I'm going to be looking for is just checking to make sure none of the x coordinates are used more than once. If I look here, do I see any x's used more than once? So this is a function then, because each x value has only one y value paired with it. Now keep this in mind that we care only about the x values when we're just looking at a function. Again, notice that each x value has its own y value. Does the fact that this y value is used more than once matter? It does not. It does not. This is still a function. To decide if something's a function or not, we're really only caring about the x's. Yes, sir. Of course. Yes, sir.
So you can have two repeated y, the y side.
Yeah, the y. In fact, the y's could all be the same, and it could still be a function.
So just that you gotta worry about the x.
We're just worried about x's when we decide if something is a function or not. Yep. There's other properties that we care about the y's for, but not about whether it's a function or not. Okay? Good questions. Let's look at this set that we looked at previously. Oops. Is this a function? No. Right? We see that we have x coordinates that repeat. So this is not a function. It's still a relation. It's still a set of ordered pairs, but it's not a function. Is everybody okay with that? Okay. Okay, so what we have here is a mapping diagram, right? So the mapping diagram is just a visual representation of really the kind of the same thing that we just saw, these sets of ordered pairs. So we're looking again to see if any of the x values are used more than once. And we also, in this case, should make sure that all of the x values get used. Which side is the x values on? The domain side, right? So 1, 2, and 3 are our x values. Is there an arrow originating from each one of those? Yes, right? So all the domains got used. How many arrows originate from each one of them? 1, so they're all used exactly one time. That means that this is a function. Okay. How about this mapping diagram? Does this represent a function? No. What's the problem? Yeah, we have an element in the domain that's not being used. Does it matter that there's an element in the range that doesn't get used? No, not whether it's a function or not. That's another property we'll talk about later to make sure that all of the range gets used. But that's not, we don't have to worry about that when we're talking about functions. Is this a function? So all the x's are used, right? Are they used just once, though? No. What's the x that's used more than once? Yeah, 1. So this is not a function. Do we feel pretty good about picking out whether a mapping diagram is a function or not? So far, this stuff has been relatively easy, right? It just, you kind of look for it, and it's not so bad. B, C, D, E, F, G is next, I think. Let's look at some pictures of graphs. So we looked at a graph similar to this before, right? When we did our examples of graphs as a representation of a relation. So if I'm looking at a graph, I want to make, really I'm looking for repeated x values, right? Visually, what would a repeated x value look like on a graph? Yes, sir?
Would they be like on top of each other, beside each other?
Or
on top of each other?
Just on top of each other, right? So for example, if I had the point like 1, 2 and the point 1, 3, those have the same x coordinates, right? 1, 2 would be like here and 1, 3 would be there. So one way that we can kind of check for this is using something called a vertical line test. I'll abbreviate that as VLT. And basically it says if you can draw any vertical line that intersects the graph more than once, that graph does not represent a function. So if we look at example G, is it possible to draw such a vertical line? I tried to make it so that that would be. Sometimes my neatness is an issue. But this is something that I would say is not a function because it fails that vertical line test. And just keep in mind that that vertical line test, all it is checking for repeated x values still. It's still the same check that we did before, but instead of having to try to translate everything into points and then look at the points, this is much easier when we have a graph because we can just look at the picture. We don't have to do any translation to another form, right? Let's look at another example. Let's say that this is our graph. Does this represent a function? Where's the vertical line that's going to intersect it more than once?
Oh.
Right? Any vertical line I draw just would hit it one time, right? So what is this? This is a function, right? Remember, the line has to be vertical. Not any line. Horizontal, don't care about. Diagonal, don't care about. Has to be vertical. That's the only kind of line we care about. So that guy's a function. Psi j. How about this graph? Yes. Yes, go ahead. Does this graph represent a function?
No.
No, right? Almost any vertical line you draw that intersects the graph is going to intersect it more than once. For example, this one. Do we feel okay there? Okay. Let's see, K is next in the alphabet. So there's our graph. Our graph is this diagonal line and a single point. Is this represent a function? I see some people saying yes. I see some people saying no. No. What's the issue? Yeah, you can draw a vertical line that goes through that point and will go through the line. It's the only vertical line you can draw that'll intersect the graph twice. But if there's just one vertical line that does it, that's enough to say it's not a function. Is everybody okay with that? Okay, that's about as sneaky as we can get on that kind of thing. But again, pretty easy, right? All we're doing is checking to see if there's a vertical line, and it's an easy check because it's all visual. There's no calculation to make. There's no symbols to manipulate. We're just looking at a picture and using our eyes. Try JKL, I think, is next. What if we have an equation like 3x minus 1, or y equals 3x minus 1? Well, the easiest way to deal with these equations is really to think about it in terms of what its graph would look like. Okay? So this one, we can use our prior knowledge, because what form do we recognize this as? This is slope-intercept form. It's y equals mx plus b. We can look at it and see that right away. What shape of graph does that give us? Well, I can see that the slope is positive, right? And the y-intercept is -1. So the graph's going to look something like this, right? Does it really matter exactly what it looks like? Not for this so much, as long as we're pretty close, right? Would this pass a vertical line test? Yeah. So we can say this is a function. JKLM, I think, is next. Do we recognize the form of this equation? I don't know if you guys did this last year or not, but this is a geometry idea as a hint to maybe jog your memories. No? That's okay. So the equation for a circle is something in this form where h and k is the center of the circle and r is its radius. Does that ring a bell? No? Still no? Maybe you didn't get that far in geometry. That's okay if you didn't, not a big deal. Okay? So if you didn't recognize that as the equation of a circle, that's okay. What could we do instead? Let's try to get the y by itself. And if we can rewrite this in like a kind of y equals yada 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 form, maybe it'll be a little bit more clear whether it should be a function or not. So the first thing I would do is I'd subtract like x squared from both sides. Everybody okay there? And then how am I going to get rid of the squared on the y? Square root both sides, right? Now, what do we have to be careful about when we square root both sides of an equation? We generate a plus or minus. Do you guys remember that? Your body language says not really, so let's explain where the plus or minus is coming from, okay? So this is just as like an aside. If I have something like x squared is equal to 4, what number could I plug in for x and get 4? 2, or negative 2, right? Because negative 2 times negative 2 also gives me positive 4. So an answer, if I have something squared equals something, I usually get 2 answers out of that, right? The positive and the negative. The only exception to that, or only exceptions to that, would be if something squared equals 0, where it's just 0 is the answer, or if it's negative, in which case there is no answer for right now. We'll fix that later on this semester and show that we can answer those questions, but where we're at right now, there'd be no answer to that. But that's why there's a plus or minus here. Is everybody okay with where the plus or minus came from? Okay. So now that the y is by itself, here's what I'm going to do. I'm just going to pick a value for x. I'm going to pick 0. Everybody's okay with that? And I'm going to plug that in. Now 0 squared is just 0, so I'm going to write 1 minus 0 there instead of 0 squared. It's okay if you put the squared in there, though, not a big deal. And then 0 squared is 0. 1 minus 0 is 1. The square root of 1 is 1. So we're left with plus or minus 1. So that tells me I have to point 0, 1 and 0, negative 1. That's a problem, right? So knowing that the graph is a circle, or knowing that here I have a repeated x-coordinate, either of those are justification to tell me that this is not a function. In general, when you do this rearrangement and you get a plus or minus, it's a good indicator that what you're looking at is not a function. Okay? Sometimes you should still pick a value for x and check, a value or 2 to make sure you're getting, 2 y's for that same x coordinate. But more often than not, that's going to be what's happening there. Is everybody okay there? And that's about as tricky as they get on something like that, where you have to unpack it algebraically a little bit. Do we feel okay doing this? Okay, good. This feels like a good place to stop. So we're going to just stop here. I think the